All right, what a wonderful introduction. Does everyone agree with me? Awesome. All right, thank you so much. So it's really exciting to be here with all of you and to tell you about food from CO2. So let me start by asking a question. Just when you think of carbon, what do you think of? Can I hear some things? Pollution, yes. Pollution, climate change, smokestacks. These are all things that you should think of when you think of carbon, definitely. But also, do you think of life? Do you think of trees? Do you think of the flowers in your garden? Do you think of yourself and your children? We are, after all, a carbon-based life form. Do you think of mangoes and cheese sandwiches? We get our carbon through our food. So carbon is everywhere. It's all around us. And we have a natural carbon cycle on this planet that recycles carbon. One organism's waste provides nourishment for another organism. The problem, and the reason why you're thinking about those other things when you think of carbon, is that our system is out of whack. We are removing natural carbon sinks. The Amazon is on fire. We are destroying our soil, which is also a carbon sink. And we're pumping carbon into the atmosphere at a rate that is faster than our natural ecosystems can handle, can recycle. So what do? There's many things that we can do, but I want to talk about creating carbon cycles. And in order to do that, let's go to NASA. Let's go back in time to the 60s and 70s during the space program, when scientists at NASA had to figure out a tough challenge. They were faced with a tough challenge as they were looking at that time, going to distant planets on long space journeys. And the question for them was, how do you recycle carbon on board a spacecraft where you don't have these natural ecosystems? How do you create a carbon cycle? So one of the ideas that they came up with involved the use of single-celled organisms, of microorganisms that could capture and convert carbon dioxide. And the process went like this. Astronauts would breathe out carbon in the form of carbon dioxide, which would be captured by these microbes, fed to them and captured. They'd use that along with energy and other sources of nutrients to grow, create food and nourishment for the astronauts, which the astronauts would then consume. And of course, the carbon would assimilate into their body because we are a carbon-based life form. But the waste would come out in the form of carbon dioxide, which would then be captured by these microbes. They would grow to produce food, and so on. And in that way, a closed-loop carbon cycle could be created. So myself and my colleague, Dr. John Reed, when we first started on this journey, we asked the question, what can you do with this process? It was sitting on the shelf. We had not yet gone to a distant planet as people. And so can we do something with this? Happily, we found out that there's many different ways of creating carbon loops. And we could use a certain class of microorganisms that could make biodegradable polymers, for instance, or that could make oils. And there's all these things that you can do and create these closed loops. And there's different ways of getting the carbon. You can get it from plastics. And so we've created a bunch of closed loops that we're working with companies to commercialize as a result. But let's go back to food. So if you want to have an impact on climate change, the fact that our modern agricultural system produces more greenhouse gases than our planes, our trains, our trucks, and our cars combined means that we have to think about how we eat. And as our population grows from the current number to 10 billion by 2050, how are we going to increase production of food in a way that doesn't increase greenhouse gases and that is sustainable? So looking at this, we can go back to the NASA process and actually figure out and learn that it's actually very similar to the way plants grow. So if you look at plants, you have an energy source, the sun, and then you have elements like carbon dioxide, and you have water and nitrogen. And then the medium of growth is soil. And you wait some number of months, and you're going to get crops from that. So similarly, with this process, you need an energy source. You can actually start with the sun as well, solar energy, but you can also use other energy sources, wind energy, hydroelectric, geothermal. And then you have elements, carbon dioxide, you have water, you can split water with that energy, and you have nitrogen. And you feed them into these microbes, and the medium of growth is different. It's not soil, it's water. And so because of that, you can scale vertically. And you can use much less land to get the same amount of output. And then, furthermore, these microbes grow very quickly, in a matter of hours as opposed to months, or as opposed to years in the case of animal agriculture. So with this process, you're able to grow food very rapidly in a way that is sustainable. And one of the things that you can end up with is a protein flour. And so a protein flour can be used for many things. It can be used to make the meat-free meats that we're hearing about. You do need a source of protein, whether it's soy protein used today or pea protein. You can use this protein flour instead. We call it air protein because this is transitioning from land-based production of key nutrients for our foods to air-based production of nutrients of our foods. And that is significantly important for a number of reasons. And one of the reasons is that you don't have to scale horizontally. You can scale vertically. Right now, because we're scaling horizontally with agriculture, the Amazon is on fire. Rainforests are being removed. Species are going extinct. Because we're making room for cattle grazing, for growing soy, for growing sugarcane, and other things. So you can scale vertically instead of horizontally, no arable land required. Furthermore, this type of process, air-based production of foods, is agnostic to the weather, the temperature, the climate, day or night, rain or shine. So in this way, one can grow food without the need to focus on climate issues, whether or not it's the right season and those types of things. And then finally, as we're scaling to feed 10 billion people by 2050, we need to do it in a way that does not produce greenhouse gases, as we see with, for instance, animal agriculture. So you can produce food continuously, rain or shine, day or night, and the amount of land that you need is significantly less than our current system. So if you had an air protein farm the size of Walt Disney World's, you would need a soy farm the size of Texas in order to get the same amount of protein. And so that goes to needing arable land and seeking arable land, and some of the consequences of that, which include removing rainforests and removing those carbon sinks, as well as the species and issues as well. So we are a crew that is growing to the 10 billion people by 2050. So we have to look at new ways of production, new ways of doing things. And one way is using CO2, not just thinking about it as a problem, which it is, because we have too much of it in the atmosphere, but how can we rethink how we can use that? How we can use that CO2 in a way that replaces the old extractive systems, whether it be for food production, or as I mentioned before, polymer production, or oil production. CO2 can be used as a resource to replace the other ways of making and producing that we've seen in the past. So I invite you all, I know that we're all here, excited to be at Verge, excited to be at this carbon summit, and you all are a part of the solution, and I thank you very much for being a part of the solution as well. Thank you.